So let's then start with this. So in any case, let me just say it like this. So, I mean, let me try to explain what this means mathematically. So these d mu vectors define some kind of a subspace, an invariant subspace, right? I don't know, let's just call it like W mu or something like that. I mean, these mu vectors, d mu vectors actually define this. So these d mu vectors define another subspace, sorry. But this is going to be some other subspace like that, but I'm going to draw it like this. And then, but the representation A is actually a unitary representation. In that case, so that's W nu. This kind of implies that these two subspaces are perpendicular to each other. We also got this mathematical relationship by some other means. We have said that, like, if there's some kind of an irreducible representation, then the orthogonal complement of this W is also an, sorry, if W mu is an invariant subspace, then its orthogonal complement, W mu perp, is also an invariant subspace. This is actually a big, huge space in here. And so therefore, all the other invariant subspaces should be under this. So therefore, this would imply that the subspace W nu should be orthogonal to this one, okay? But I mean, it is that property of the unitary representations that somehow implies this orthogonality, okay? So the first property, you can think of it as like, as an expression of this fact. So if you have two invariant subspaces corresponding to different irreducible representations, then they are orthogonal to each other. They are perpendicular to each other. But again, this is only because this representation A is unitary. Otherwise, if A is not a unitary representation, then the only thing that you can say is that these two invariant subspaces are different from each other, okay? So it is this first property. The second property, when the two representations are the same, in that case, these two subspaces do not need to be orthogonal to each other, because somehow, I mean, an irreducible representation may appear many times in the decomposition. In that case, you can actually have these kind of possibilities as well, that these two subspaces might be making an angle with each other. Okay, and there are also problems like defining these subspaces as well in a unique way. We cannot define them in a unique way, actually. In any case, so again, it's important in here that, for example, let's say F2 is always perpendicular to E1. So the first vectors are always perpendicular to the second vectors, okay? So as a result, this is basically what we can say. So let E1 dot 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 ED mu is an irreducible set. Then all of these vectors are mutually orthogonal. Right, so that's the first one. All of these vectors are mutually orthogonal, and two, all of these vectors have the same length. It's a corollary of the first, the thing that we have said above. because there's nothing new in here, right? It's just applying this to a given irreducible set. The reason is that I can define this xij as like ei dot product with ej. So because of the previous problem, this is like c times delta ij. And this then implies that, first of all, this E1 squared is equal to E2 squared. The length squares are whatever. They are all equal to each other. So that's the second property. So C is basically the length square of these vectors. And the first property basically follows from the fact that this E1, E2 dot product is equal to 0, but let me say etc. Okay, and that's basically what it says. I don't want them to be normalized, but normally, I mean, we would like to use a normalized set. So therefore, this number C will usually be equal to 1. But I'm talking about a general possibility here. Right. I don't know if you have any questions, because this is kind of, I think the essential point in here is that we are defining some concept in here. The concept itself is important. The proofs are a little bit confusing and it's kind of long, let's say, but it is straightforward. So as a result, I'm not going to go over the proofs. So as a result, I'm just going to ask you to prove this yourself, all right? So the rest basically follows easily. Okay, so there's a new definition now. Okay, so let's say I'm talking about the mute irreducible representation. Let's say that ij are matrix elements, ij matrix elements. Meaning that I and j are basically numbers from 1 to d mu, right? That's what I'm saying. So for that matrix element of that representation, I'm going to define an operator, p mu ij, right? That's the definition. It's defined as d mu divided by the order of the group, and then sum over the group elements of, I'm going to write down the complex conjugate of the matrix elements of the mute representation corresponding to different elements, and then A of G. Okay. This is not a projection operator, but it's an operator that we are going to use later, right? So that's our first definition. Okay, so I'm basically taking a linear combination of these representation matrices. What linear combination? Well, it's a linear combination where the coefficients are basically the matrix elements of that particular representation, okay? So, I mean, you need to know the matrix elements of irreducible representations, not just the characters, but the matrix elements as well. And this is perhaps a difficulty. When mu is equal to nu, is this that F is the same as E? No, it doesn't have to be, okay? I mean, if I have like two different sets transforming like the same irreducible representation, I still have the same property, okay? In general, it's like that. But here I applied this result for the case where these two irreducible sets are the same, right? This is basically an irreducible set. I apply this rule for the case that these two sets are the same. Okay. But the previous theorem is actually general. I mean, you can show it yourself and then deduce that this is basically, this has to be the case. In any case, what happens in here is this, if I multiply these two operators, so this is just a representation matrix A of H, let's say, P mu ij. Okay, so I don't want to do the calculation in here. There are lots of steps in here, but you can show that that's equal to sum of L u mu of Li of H P Lj of mu. Right, so that's basically a theorem. That's the first theorem. I don't want to show this. I'm going to ask you to show, right? Just show by yourself, but I can quickly explain what the idea is, right? I mean, if you just apply this to that expression, that's what you're going to get. So let me actually do this quickly, right? So something like that. So that's A of H applied on P mu ij. So that's d mu over G, sum over the group elements of u mu of ij G star, whatever. I have A of H multiplied with A of G in here. Okay. I then use the fact that this is a representation, so I replace this with A of HG. So I'm going to do this. So let me just erase everything and then write A of HG in here. Okay, so that's the first step. The second one is I just make a change of variable. Just call this as G prime, which is H times G. So that means that G is equal to H inverse times G prime. And do the summation over G prime. Okay. This is a trick that we have used before. H inverse G prime complex. There's a complex conjugate in here, right? And then A of G prime in here. Next, use the fact that this is a representation. So therefore, this is like UIL mu H inverse ULJ G prime mu, whatever. There are these complex conjugates as well. So just expand it like that. And then you're going to have this G prime summation in here. That summation is going to give us the projection operator. And then you simplify this and then show that this is equal to ULI mu of H, right? So once you do this, then you're going to get the result. But I'm just going to ask you to do this yourself, right? Because, I mean, if I go over to these kind of details, then the essential ideas will be lost. Okay, but that's basically the expression, which then tells us the first important thing, right? So just keep in mind that, I mean, we have the representation matrices to start with, right? We have a representation, so we know all the representation matrices. We know all of A of G. And if we also know the matrix elements of the irreducible representations, then I can define these operators. Again, these are not projection operators, but I'm just going to call them as operators, right? So in any case, what does that imply is this. So the idea is this. So let, I don't know, let phi be any vector. It has to be non-zero, right? But I mean, for usefulness, but what I'm going to state is going to be true if phi is also equal to 0. So in that case, the set, right, P1J mu applied on phi. So let me write it down like that. So let's define E1 like this, E2 as P2J applied on phi, and so on, right? You just define these d mu vectors in here. Okay. So as a result, the set of vectors is an irreducible set transforming like the mute irreducible representation. Okay, so in any case, what's the use of these operators? Basically, if I apply these operators to any vector, but it's the same vector in all of these cases, then I can produce a random irreducible set that transforms like a particle irreducible representation. So it may turn out that these vectors are all equal to 0. If one of them is 0, then all of them has to be 0. We know that. But by using this property in here that I boxed in here, right? This property, you can show that this is an irreducible set. Okay. Right. Basically, this is how we use these operators. Okay. So this is quite easy to show. The next thing that I'm going to show is a little bit more complicated. So, I mean, this P mu has like 2 sub-indices in here. I'm not changing J value in here, right? So the J value is the same in all of these cases. I'm just looking at vectors for different I values, if you want, right? So, but what's the use of J in there? I'm just going to show it like that. Let's see. First of all, I'm going to argue this. So let's say P mu ij. I'm also going to ask you to show this. So it's just the product of 2 such operators, right? It appears that this product is equal to 0 if the representation labels are different. So if they belong to different representations, the product is always equal to 0. The product is also equal to 0 if J is different than K. So there's a delta JK in here. And whatever, there's then therefore P mu of IL, right? I'm going to ask you to show this one as well. So interestingly, we are going to use the orthogonality property of the matrix elements of the irreducible representations in here. But I don't want to go into this again. Okay, so the idea in here is this. Basically, I'm just going to show it like that, right? Let E1 ED mu be an irreducible set transforming like mute representation. Like the mute irreducible, yeah, whatever. I have an irreducible set corresponding to an irreducible representation. Just show that. You can show that easily, no problem with this. Again, if I apply Pij to Ej, I'm going to get Ei. Okay, I mean, this is basically the meaning of these operators. So these are operators that basically map a given vector in an irreducible set to other vectors, right? So you basically do it with these kind of things. So in Dirac notation, I would basically write this P mu ij as like Ei ket EJ bra product, right? It's a vector that transforms EJ into EI. But unfortunately, this is not exact because, I mean, there might be many different invariant subspaces. So as a result, I have to sum this over the invariant subspaces. So this part is a little bit tricky. So as a result, if you get confused about this, just forget about it. It's not something that you need to know. That's not that important. So as a result, I'm just going to erase this. Okay. So that's the first thing. The second thing is this. What happens if I apply this to, let's say, a vector where the label is not equal to j, right? So this is pij. So these two labels are different from each other. So the result is 0. It's basically consistent with this expression in here. And then finally, we have this. So if I apply the operator corresponding to a different representation for EK, so let's say is 0 if mu is different than mu, right? So as a result, if you think about these operators, P operators, on vectors of an irreducible set, when they act on the vectors of an irreducible set, they basically have this property. The result is almost always 0. Exception is this, when the representation, they belong to the same representation, and these two indices are the same, in which case this P operator basically converts. Okay. I think this is enough for that property. I'm just going to show something else. Okay. Sorry, I was thinking about something else. Sorry about that. Yes. So in any case, the property that I'm going to talk about is this. So therefore, basically, PII, sorry, applied on EI, that's equal to EI. Okay, so it basically converts a vector to itself. But if it is applied to, let's say, a different vector, EK, we get 0 if I is different than K. So, I mean, it's just a particular case in here. In any case, I just defined some operator that I'm just going to call with this label P mu. It's basically a sum over PII. Sorry, it's a sum over PII. So as a result, this is like P11 mu plus P d mu d mu. All right. If you want, this is like trace, but it's not the trace because these are sub indices of some kind of an operator set. So as a result, this is something else, but it looks like a trace, right? In any case, so these P mu are called the projection operators, but their property is this. So let's say it like, I'm just going to box this, right? If E1 dot 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 ED mu is an irreducible set transforming like muth irreducible representation, then P mu EI is equal to EI. So therefore, basically it acts like identity on these vectors. But the other ones, let's say P mu EI is equal to 0. right? This is if the representations are different from each other. But this basically comes from some other properties that I have mentioned before. In any case, so this is going to be important for us. So as a result, I'm just going to look at the properties of this p mu operators, right? So what's important in here is that for any irreducible set that belongs to the mu's irreducible representation, all of the vectors in that irreducible set are invariant under p mu, which means that any linear combinations of them are invariant, which kind of means that the all vectors in an, I don't know, in invariant subspace that corresponds to that representation will be invariant under these. Whatever, I'm just going to just show some other properties in here. So let's say it like this. So let's just remember this Pij mu, that's equal to d mu divided by g, sum of the group elements of uij mu g complex conjugate a of g, right? Let's remember this. In the case of p mu, I'm going to sum them up. So in that case, you can see that this is like, let's see, there's a summation over I, therefore, of this one, the matrix elements in here. Okay, so let me actually write it down like that. So since I have as coefficients these matrix elements in here, when I define the operator p mu, I have these ones. But this is just the character, so therefore this is chi mu of g complex conjugate. So I only need the characters in here. Right. So, I mean, if you know the characters, then you can define these operators. Okay, so that's the important point. And so as a result, I'm going to box this. So d mu over g is in front. I need to sum over the group elements, not the conjugacy classes, right? So even though all group elements in the conjugacy, same conjugacy class, they have the same character, I know that the representation matrices are different. So as a result, I need a sum over the group elements in here. So let's say it like this. Therefore, p mu can be computed by using the character table. All right. So the character tables that people publish is useful for that purpose too. Again, you need to know the representation matrices, obviously. And then by taking their linear combinations with the characters, I can define these operators. So that's the first one. Second property is this. So yeah, that's the first property. So this is the second property. These are Hermitian. These are Hermitian operators. I think I'm going to explain the meaning, perhaps not today, but on Wednesday. There's some kind of a geometric meaning of this. But I can show it like this. So just take the Hermitian conjugate of this. So p mu dagger would therefore be like d mu over g, sum of g. So therefore, this is chi mu of g. And then the Hermitian conjugate of a of g. Okay. But I know that this is unitary, so therefore this Hermitian conjugate is the inverse of this matrix in here. And I know that A is a representation, so therefore I can place this inverse inside. Okay. And so as a result, I can do a second summation in here. So I just change the label. So as a result, write this thing down as A of H. And so therefore we have chi mu of the H inverse in here. It's a summation over H. And at this point, you can then argue that the character of the inverse is equal to the complex conjugate of the character of the element. So as a result, by erasing this inverse in here, I can replace it with the complex conjugate. Okay. Again, this has something to do with the unitarity of that irreducible representation, but I'm going to leave that to you. And so as a result, you can then show that this is equal to P mu. It's a Hermitian operator. Okay. Again, this has to be unitary. Otherwise, it won't work. P mu is Hermitian. Second property. P mu times P mu, that's equal to delta mu nu times P mu. Again, show this. I mean, it basically follows from the previous property that we have written down for the other P operators. I don't want to go into this, but what's important in here is the geometric property. Okay.
John, does this tell us these operators are, projection operators are nilpotent?
It's a nilpotent and projection operator. Yeah,
okay.
Projection operators are nilpotent.
Yeah, okay.
Right. So therefore, this basically implies that the square of each of these operators is equal to themselves, P mu, and the product of two different operators is equal to 0. Okay. So in any case, so we basically have an operator, sorry, a set of operators, one for each irreducible representation, where each operator is Hermitian and their square is equal to themselves. So this they say that this is the idempotent property. Okay. So this appears in many times in many places, even in quantum mechanics. I actually explain quantum mechanics with these operators. So these are called projection operators. So we say that an operator Q, let me use Q, is called an orthogonal projection. Or just projection. Since in quantum mechanics we always work with orthogonal projections, people usually just call them, for economy, just call them as projection operators. Right? An operator is called an orthogonal projection or just projection if it satisfies these two properties. It is Hermitian, so Q degree is equal to Q, and it's idempotent, so Q squared is equal to Q. Idempotent. Well, why do we call them, these operators satisfying these properties, as projection operators? Because they actually correspond to something that we call as a projection. So it's something like this, right? So there's some kind of a subspace in here. So I'm just going to call this subspace as like subspace W. Right? Take any vector in here. I don't know, let's call it as V. And think about this operation in here. So just draw a line from the tip of the vector to the subspace, okay? I mean, think of it like this. So there are like, think of it like light is coming from this direction, let's say. I mean, think of it as a three-dimensional picture. Light is coming from this direction, and we are looking at the shadows of vectors on that subspace. So as a result, this vector has some kind of a shadow in here, and this is called the projection of V, right? And I'm just going to call this as V parallel in here, right? And this is the perpendicular component. So you can then think of it like I decompose V into these parallel component and a perpendicular component. So let's say it like this. Therefore, V is equal to this parallel component plus the perpendicular component. In any case, so we have this idea in here. So in that case, what I'm doing is like projecting this vector onto that subspace. So that's an orthogonal projection. There are projections which are not orthogonal. So in that case, for example, think of it like this. If I have some kind of sun in here where the light rays are coming at an angle, let's say, in that case, a vector in here might have a shadow like that. This is also some kind of a projection, sending vectors to some other vectors in here. So let me call this as like V prime in here. This is a projection. So let's say this mapping in here from V to V prime is a projection, but not an orthogonal projection. Okay. I mean, to distinguish between an arbitrary projection and an orthogonal projection, let me just give this example, right? In that case, that angle in here is not 90 degrees. An orthogonal projection, you can think that, well, the light rays are coming from the top. So therefore, the corresponding projected vectors are perpendicular to these light rays, right? You can then think of it like this. So that's an orthogonal projection. Okay. What happens is that this mapping in here, so that sends the vector V to the projected vector, is a linear map, right? This is linear. And since it's linear, it can be expressed as some kind of an operator applied on this V. And this operator is called the projection operator, okay? It turns out that for orthogonal projections, this operator satisfies both of these properties. So Q is orthogonal. Let's say it like this. So Q must satisfy, in that case, these two properties satisfy. That first of all, its square should be equal to itself. This actually means that if you have a vector which is already projected, and if you take the projection of this thing, you get the same thing, right? I mean, taking twice the shadow of something, right? You first take the shadow of a vector on the plane, and for a vector on the plane, its shadow is itself, basically, right? That basically corresponds to the fact that this is taking a projection. Now, the orthogonality property is basically expressed by the Hermitianness. Okay. So as a result, this is a projection. Basically, it's an orthogonal projection. So as a result, we need to have these two properties. On the other hand, for an arbitrary projection, we have this. We only need this relationship. So in that case, there's some kind of an operator in here that gives us this projected vector. So let me say it like this. R needs to satisfy the idempotent relationship only. Only, right? So that means R squared has to be equal to R, but it doesn't have to be Hermitian. Okay. So this is basically geometry. What does it mean to take a projection? Okay. What does it mean to take a projection? It essentially means that as a linear operator, I can describe it as some kind of a linear operation where R squared is equal to R. This is the idempotent relationship, okay? But if I also insist that this is an orthogonal projection, in that case, the operator should be idempotent, but it also has to be Hermitian. I don't want to show this, prove that this must be so to you, but it can be shown. I mean, it just involves some kind of a symbolic manipulation of these inner products and things like that, but I don't want to go into this, all right? I'm just telling you that this is the case in here, all right? But this is one aspect in here. So that's the orthogonal projection. So as I said, I mean, a projection and an orthogonal projection are different things, essentially. An orthogonal projection is just a special kind of a projection. But as I have said, since we always meet these orthogonal projections, especially in quantum mechanics, we just call them as projection, right? It's just an abuse of notation, abuse of terminology. But whenever I say projection, just understand that this is an orthogonal projection. Okay. Why we have this? So what it appears is that there are these two eigenspaces in here. So let me just say it like this. So it appears that all the vectors in that projected subspace in here are eigenvectors of Q with eigenvalue 1. Because whenever I project a vector on that subspace, by this process, I get the same vector, which means that the vectors are eigenvectors. Okay, but there's another subspace in here, so that's the orthogonal complement, so that's W perp. These are vectors where when they project it, they just project to 0. And so therefore, these are also eigenvectors. So these are the eigenvectors of Q with eigenvalue 0. Okay. So as a result, there's some kind of a one-to-one correspondence between subspaces and projection operators, orthogonal projection operators. Because I mean, for each subspace, I can define an operator like that. And for each operator, I can define a subspace like this, basically by using these mathematical properties. Essentially, this correspondence is one-to-one, okay? So for every orthogonal projection, the corresponding eigensubspace is the subspace where we are taking the projection. So this is actually an alternative way of investigating this geometric concept of taking projection by using operators only. So the geometry is important, so that's something that you have to keep in mind. In any case, so on Wednesday, I'm going to continue on that topic, so the orthogonal projections. But the essential idea in here, when I summarized every mathematical detail in here, we are going to go back to these. Basically, what we are doing is like, by using representation matrices, we are defining projection operators, which basically gives us all of these invariant vectors in invariant subspaces by applying some certain procedure, right? So as a result, at the end, that's what I'm going to say. These are going to be useful, so that's why we are studying it. All right, let me stop here. On Wednesday, I'll be continuing from that point.